Welcome everyone. For today's prep, we're going to see how units work with derivatives. And before we get to the units part of this, we're going to introduce a little bit of terminology, and that is rates of change. So when we talk about a function, a lot of times we're interested in how our function is changing. So what we've seen so far, we've seen if we have a function, how to calculate the derivative of that function. Well, we're just going to introduce just a little new terminology here called the instantaneous rate of change. This is the rate of change we're going to be primarily interested in, the instantaneous rate of change. So this is telling us essentially how fast our function values are changing at one specific point on our graph, at one specific x value. And the way we can calculate this instantaneous rate of change is by first calculating our derivative and then just plugging in that x value we're interested in. So whatever that number a is, plug it into the derivative. So the derivative essentially is telling us, giving us information about how fast our function is changing at any point along the curve. So if we had a graph, so let's say here's the graph of a function, and we're interested in a point P. So we're interested at one specific point on that graph. Well, we can think of the derivative, or this instantaneous rate of change. Again, it's just really measuring the slope of the tangent line. At point P. And maybe let's give point P some coordinates here, a comma f of a. So let's write that down. So let's say a is the x value we're interested in, and so the y coordinate on our curve is just the function value evaluated. All right, so that's all this instantaneous rate of change, just another way to describe how fast our function is changing. So how fast our function is changing at one specific point, well, that's just the slope of the tangent line. So if our tangent line is pointing up, then our function is increasing. If our tangent line is pointing down, then it's decreasing. Or if our tangent line is flat, well, then there's no change. Okay. So that's the instantaneous rate of change. Just measures how fast our function is changing at one specific point. Sometimes, though, we're also interested in the average rate of change of our function over an entire interval. So if this is the case, if we're looking at an entire interval of x values and we want to know how much our function, on average, how much our function is changing over that entire interval, well, we have this formula here, f of b minus f of a over b minus a. And this is, we've kind of seen this one before. This is just our regular slope formula. So a way to think of this average rate of change formula, this is just change in y over change in x. So if we go back over to our graph, we've got our point P that we're interested in. So this is looking at x equals a. And what this average rate of change is doing is we're looking at an entire section of the x-axis. And so we're going to some other point Q. And this will have x coordinate b, and then the y coordinate, we just plug b into our function to get. So this second point Q, let's extend that down. We're going to x equals b. So with the average rate of change, what we're doing is we're looking over this entire little section of the x-axis. And essentially what the average rate of change does is it takes all of those instantaneous rates of change at every point inside that section of our curve and averages them all together. And it's giving us the average rate of change. So there's some sections where maybe our curve it's increasing, but maybe it's a little slower. And then there's other sections where maybe it's increasing at a faster rate. So what the average rate of change does is it kind of averages those sections together and gives us the average result. So geometrically, this is just the slope of the secant line. Just our regular slope formula connecting 2 points. So average rate of change, what it's doing is it's averaging all of those kind of instantaneous rates of change together inside that interval. And for an instantaneous rate of change, we're looking at how much our function is changing at one specific point. So we're looking at one specific point. And that's really just the slope of our tangent line. So a little bit of new terminology here. And why we mention this is because our secant line formula kind of gives us an idea for what the units are going to be. So what is the units for our derivative? So when we talk about rates of change, when we talk about derivative, what are the units for our derivative? Well, if we kind of go back up to our little slope formula there, it's the change in our function value, change in y, over change in x. So the units for f prime are going to be the units of our function value, so that was the numerator there, divided by whatever the units for our variable x are. And so our average rate of change is going to have this units, and our derivative is going to have these units as well. All right, so let's try an example. We're just going to look at one. So this is an example. Let's read through it first. The account balance for a savings account can be modeled by function a of t. So we have function a of t down here. Variable t in this formula represents the time since the initial deposit was made, and t here is measured in years. And function a of t, the output of this function, represents the account balance at time t. And this is measured in dollars. So this account balance function, let's read through the formula. It's 1,000 plus 150t plus 11.25t squared plus 0.5625t cubed. So a little bit tricky of a function here. We want to know, first part of this, how fast is the account balance changing after 10 years? So when we see wording like this, how fast and changing, we should be thinking instantaneous rate of change. And we're looking at one specific moment in time at the 10-year mark. All right, so this is really asking us for an instantaneous rate of change. So we're going to calculate, first of all, the derivative. So let's differentiate this function. And we've got a few terms here. So we've got this constant term, this 1,000. So when we differentiate that, that's going to be gone. That's just a constant all by itself. So then we go on to the next term, 150 times t. What's the derivative of that? Well, it's just the 150. Okay. Then differentiate the next term. So we do a little bit of power rule. We get 22.5 times t. And if we differentiate the last term, we do, again, that 0.5625. That's just a constant multiple. So even though it's a little bit trickier than maybe some of the other constants we've seen, just a constant multiple, and we're differentiating that power function. So let's take the 3, bring it down, multiply it with those terms in front. And maybe you need a calculator for this, but let's see if I can do it. What do we get? We get 1.5, 1.6, 8, 7, 5. Hopefully that's right. I think it is. T squared. Okay. So that's our derivative. So we want to know how fast this account balance is changing at the 10-year mark. So this formula, what it does is this tells us how fast our account balance is changing at any time t. We want to know specifically when t is equal to 10. So to do that, we're just going to evaluate. So we're going to plug 10 into this formula. So wherever we see a t, got one here, got one here, we're just going to replace it with 10. So we get 150 plus 22.5 times 10 plus 1.6875 times 10 squared. And let's see if we can simplify this. So maybe we need a calculator, but we got some powers of 10 here. So multiply that, we end up with 225. And 10 squared is 100. So we can just move the decimal place over a few. So we end up with 168.75. And let's see what we get. So we're going to get from the first two terms here 170 or 375. And then if we add in the 168.75, let's see what we end up with. So, well, we're definitely going to end up with 75 as our decimal. And then 8 plus 5 is 13. So 543.75. And maybe check me. All right, so that's our value. So the question is, what are the units on this value here? So again, when we did this, we calculated the derivative. And what are the units for our derivative? Well, it's going to be the units of our original function divided by the units of our variable. So in our case, for this problem, the units of our original variable, so the units of variable t are years, and the units of our function are dollars. So when we calculate the units for our derivative, it's going to be the units of our function divided by the units of our time, of our t. So the units here are going to be dollars per year. Or if you wanted to write the per, you can write that as a division sign. So what this is telling us, and let's kind of look at the second part, we want to know, is the account balance increasing, decreasing, or not changing at this time? Well, we found that the derivative value here was 543.75. So the fact that this is positive is telling us that our account balance is increasing. So A of t is increasing, since that derivative value is positive. So a way to kind of interpret what this is telling us, this 543.75, a way to interpret it is if we were to, so we have our account balance, our money's sitting in our account and it's growing over time, apparently. So our account balance is increasing. So right now we're looking at the 10-year mark. So a way to interpret what this derivative value is telling us is if we were to let our account sit for one additional year, we would expect then by the end of year 11, or at the end of year 11, that we would have about 543 extra dollars in our account. So you can think of this as really over the next year, we would expect to have 500 and approximately $543 in our account. So that's a way to kind of interpret what this derivative value is telling us. So this is telling us kind of what to expect over the course of the next year. So it's telling us, well, first of all, our account balance is increasing at this time because the derivative is positive. And it kind of gives us a way to estimate over that next year, we would expect to have approximately $543 extra in our account. All right, so we're going to try some more examples like this in class where we kind of look at the units of our derivative. So we'll see you then. Bye-bye.